Okay, today we are going to learn about boosting. Boosting, as I mentioned before, is not a classification technique. It's a meta algorithm that can be applied to any classifier. So we have learned so many classifiers so far, different algorithms. Boosting can be applied to those algorithms. So in theory, if you have a classifier which works slightly better than chance, suppose that you have only two classes. You are doing binary classification. Okay? So chance would be just flipping a coin. If I just flip a coin, half of the time I'm going to decide class 1, half of the time I'm going to decide class -1. Suppose that you have a classifier which works a little bit better than this, like 51% of the time this class and 49% of the time the other class. In theory, you can boost that algorithm and make a really good classifier out of that. So let's see how boosting works. So I try to explain boosting in a very intuitive form first, and then I go to mathematics behind boosting. So intuitively, that's the idea of boosting. You have a data set. So that's my sample. And I learn a classifier. Let's call it H1X. Okay, I learn a classifier using one of the algorithms that we have learned so far. This classifier is not a perfect classifier. Some of the points are going to be classified correctly. Some of the points are going to be misclassified. Okay? Then I'm going to reweight my points in this data set. Give more weights to points that have been misclassified. Okay? So basically, I'm going to make a new data set which is weighted. So I'm going to make a weighted sample and then another classifier. And this classifier, as we are going to see the detail, is a classifier which gives more attention to points with more weights. So the points that have been misclassified in the previous step are going to get more attention now. So I'm going to learn a classifier for this weighted samples. This H2 also is not going to be a perfect classifier. Some of the points are going to be misclassified. Again, I'm going to reweight this data set, and give more weights to those that have been misclassified. And I'm going to repeat this process m times. So basically, I have learned m classifiers. Only the first classifier was on a data set with equal weights. All of the other classifiers are learned on weighted samples. Now, I'm going to take a weighted average of all of these classifiers. So basically, my final classifier is going to be alpha j, 8j, x. Okay? So that's my new classifier or my new estimate. For j equal 1 to m. Okay? And in a setting that my data points are from class -1 and +1, I'm going actually to compute the sign of this weighted sum. So my final decision would be based on somehow the majority or some sort of committee voting on examples according to this scheme. Okay, that's the idea of boosting. Okay, so I'm going to write down the algorithm of boosting, and then we'll mathematically see why it works. But I think intuitively it makes sense, that if you want to make a decision based on a classifier and some of the points have been misclassified, means according to this classifier they haven't been treated fairly. So give them more weight, and learn a classifier which classify those points correctly that have been misclassified. And then take a vote among all of the classifiers that you have learned. Okay, that's the idea. So let me erase this. So the setting, as usual, is that I have n data point, and yi could be from class -1 or class +1. So the boosting algorithm, boosting has many different variations. The boosting that I'm presenting now is the original one. It's called Adaboost. But then there are many different variations of that with slight difference. So the first step of Adaboost or boosting is to set equal weights to all points. Okay? So I'm going to set equal weights wi equal 1 to n for all I in the data set. And then I'm going to do the following. For all j equal 1 to m, I'm going to learn a classifier, and this classifier would be hj of x, which is basically arg mean of a cost function. I'm going to minimize the cost function and learn a classifier, and this classifier could be anything. Could be tree, could be naive Bayes, whatever. Okay? So I'm going to learn a classifier by minimizing Lj. So Lj that we used to minimize in the past had a form of usually, some sort of measure of misclassification. So we had, say, for example, summation over all points that have been misclassified. Right? This is the number of points that have been misclassified, and we used to minimize this or minimize this. Right? Now, I'm going to just modify this a little bit and make it weighted. So in this setting, all of the points have the same weights. But I'm going to give points different weights. So basically, I would like to minimize this, divide by summation of weights. So that's going to be my Lj. So a weighted cost function is going to be minimized, and I'm going to learn a classifier. Okay. Now, some of the points, you can see that in the first step, this W is 1 over n, so it's going to be what we used to do regularly, Some of the points are going to be misclassified. I'm going to give them different weights, and I will define, some weight here. We're going to see why this weight has been defined this way, which is log of 1 minus Lj divided by Lj. And then Wi is going to be Wi times e to the power of alpha j I yi not equal h xi. Okay. See, so we minimize this cost function. We learn a classifier. Some of the points are going to be misclassified. I'm going to compute this alpha, but see what this alpha means, actually. This L is my cost function, right? If I'm flipping a coin, what would be the value of L? How many points are, what's the percentage of the points that are going to be misclassified? If I'm 50%, right? So if I'm flipping a coin, this Lj is going to be 0.5, right? And if I have a classifier which works better than chance, it's going to be less than 0.5. And a perfect classifier would be 0. So in worst case, this is 0.5. 1 minus 0.5 divided by 0.5 is 1. I have log of 1 is 0. So in the worst case, this alpha is 0, right? In the best case that I have a very good classifier, this is going to be a large number. And it's going to be log of a large number. So it goes to infinity if L goes to 0. If I have perfect classifier, this goes to infinity. So this basically has, a form like this, that if this is Lj, this is 0.5. At 0.5, it is 0. And when it gets better, it goes to infinity. It's like this. That's alpha. It means the better the classifier is, the larger the alpha is going to be. Okay, now look at this scheme for reweighting all data points. We are going to reweight data points only if the point has been misclassified. For the points that haven't been misclassified, this quantity is 0, right? If the points have been classified correctly, then y is equal to hxi. This is 0. And then I have e to the power of 0, which is 1. So w, the new w would be the old w. I'm not going to change w. But if the point is misclassified, then this is 1. And the weight will be multiplied by e to the power of alpha. Okay. So suppose that the classifier that I used was just random classifier. I just flipped a coin. So alpha is 0. I multiply w by e to the power of 0. Means I don't change the weight at all. Okay? But if it was a good classifier, e to the power of alpha is going to be a large number. And I'm going to give a large weight to this point. So it means that if this point has been misclassified by a bad classifier, it makes sense. I shouldn't pay too much attention in the next run to this point. A bad classifier misclassify all points, If I flip a coin and this point has been misclassified, don't change the weight. That's what we expect by flipping a coin. We don't expect to do anything good. But if it was a good classifier and misclassified this point, then give a weight according to the goodness of this classifier. The better this classifier was, give it more weight for the next run. Okay? Does it make sense?
But aren't we kind of overfitting when we do that?
No.
We won't be?
No. What's the good things about boosting is that it doesn't overfit. It doesn't mean that it doesn't overfit at all. It's quite resistant toward overfitting. That you run it for a long run and data doesn't overfit still. It has a very good generalization bound usually. Okay? So we are going to repeat this for m times. My final classifier, as I mentioned, would be weighted sum of all of these classifiers that we computed. Okay? Or you want to call it H. That's your final class. You know, I have e to the power of this log. So basically, this weight is going to be just 1 minus Lj divided by Lj. So it's again having this form, but I think more, it's sharper than this. Okay, this is explanation of boosting, you know, in a intuitive way, and I think it makes sense, you know, intuitively. But mathematically, why it works, and why it works so good, you know, because boosting has really good performance, you know, in practice. It's very good performance. It was sort of mystery for a while, you know, after proposing boosting, and people start to think why it works, and they came up with many different theoretical justifications for boosting that I'm going to tell you about one of them today. So one way of thinking of this algorithm, boosting, is to looking at boosting as fitting an additive model. So we have seen one additive model at least in this course, RBF network. So if you recall, in RBF network, we had, you know, a d-dimensional data, and then we had m phi, and then we had an output, and the output was a weighted average of this basis, right? We had m bases, and the output was a weighted average of this basis. So basically, our function was a sum over all beta j phi j. And we solve this in closed form. In general, you know, that's just one example of additive model. Additive model means that you have different bases. You map your data in a space with some bases, and then you try to learn a function as a weighted average of those bases. Okay. In general, you know, if we have a cost function L, so L, y, and f of x, you know, could be different things, you know. In this case, you know, that was our cost function. So we had some matrices, and we minimized the squared of Frobenius norm. But in general, suppose that you have a cost function, and this cost function needs to be minimized. For additive model, basically you have to go over all data points, and for each data points you have to minimize the distance between yi and a summation of this form. A summation over j of beta j phi j xi, and phi has usually a parameter. So we have to minimize this. And we have to learn beta, and we have to learn the parameters of this model. And sometimes we have to learn the form of this function as well. So in the case of RBF, it was easy to solve because we made some simplification assumption. In general, it's not easy problem, you know. You want to minimize this cost function. At the same time, you want to find this coefficient. You want to find the form of this basis function, and you want to find the parameters. Make it even simpler if the form of the cost function is known. Still, it's a hard problem, you know, to find the parameters and to find the beta at the same time. In RBF, the basically simplification assumption that we made was that we assumed that this gamma is known. You know, we set gamma for all of these basis functions ahead of time. We just solve for beta. If you want to solve it for both, it's not easy. You can solve it for one at a time. But solve it for both of them at a time. It's possible, but it's not easy. So there are different ways to solve a problem of this form. One, by making simplification assumption as we made. And another one is to approximate this function by learning one of these basis functions at a time. Suppose that I have this model, but I assume that the data can be approximated only by this base function. And then I fit a model. It's not a good model, it's not really close to my labels, it's far. I have a residual. Then I try to fit the residual. So the remaining, the error, I'm going to fit it by the next basis function and add it to the previous one. So I make an additive model, but gradually, and at each step, I fit only one of these basis functions. Then I have an error, I fit the second basis function to take care of this error. And then I have some error, I take the third one up to the last one. Okay? That's the idea. And this is a way, it's called forward stage-wise additive modeling. Forward stage-wise additive modeling. Okay, in forward stage-wise additive modeling, the assumption is that I have a function like f of k of x, and this f of k of x is summation of j equal 1 to k of beta j phi j x and some gamma for all k that are less than equal to m. And at each step, to compute, say, for example, let me call this k plus 1. At fk plus 1, I have fk plus some beta phi x gamma. So at each step, I assume that a summation up to the previous iteration is known. All of the parameters have been learned. All of the coefficients have been learned. I just need to learn this coefficient, this parameter, for this step. Does it make sense? Is it clear? Any question here? For example, if Lyfx is y minus fx squared. This then you want to fit fk plus 1, for example. You're going to have at each step, you're going to have yi minus, say, fj would be fj minus 1 of x minus some beta times phi square. This is your function. You assume that this has been learned. This is unknown. Okay? And in this case, you can assume that this part is just your residual that is known, the error of the previous step. And the only thing that you need to fit or you need to learn is just, if I call it Ri, residual, you need to minimize this. This is known. I need to just learn this coefficient and this parameter for this step. Okay? This strategy is an approximation to learn additive model, which is called forward stage-wise additive modeling. Yes?
Just wondering, if the beta in the middle line is actually beta k plus 1, so as in...
This?
Yeah,
Yeah, that's beta k plus 1, but to make our notation, simpler in next, derivations, I just don't put any. Just assume that in each iteration you need to learn a beta and a gamma, which belongs to that particular stage.
and then in the next step you added...
When you learn it, you add it to this fk, and you have fk plus 1. You go for the next step, and you need to learn another one, and then you add it and go on. Okay? Well. Any question? It's important to understand this part because the whole derivation which comes after is based on this. So if there's any ambiguity here, let me know. Okay. So now the idea is that boosting, in fact, feed an additive model to the data when the bases are classifiers. So as if we are fitting an additive model to the data, and these are our bases, classifiers of our bases, but we do it using this algorithm, forward stage-wise. So at each step, we learn one of these basis function, and in next step, we just learn the other one. Okay? That's the idea. So how we can see that? So in boosting, the cost function, L, is e to the power of minus y f of x. That's the cost function that we are trying to minimize. This is not this cost function, for example, Adaboost. This cost function makes sense, because y is -1 or +1, and f is -1 or +1, or h is -1 and +1. Let me call it h, because it's classifier that we have. It's -1 or +1. So if we haven't misclassified, if y is negative and h is negative, then yh would be 1 if both of them are negative. If both of them are positive, again, it's going to be 1. So in the case that we classify it correctly, it's going to be e to the power of -1. In the case that we classify it in a wrong way, it's 1, but it's -1. Or this is 1, this is -1. It's going to be e to the power of 1. So it's going to be large when we misclassify. Going to be small when we classify it correctly, right? So by minimizing this, we can learn a classifier. So it makes sense to have this as our as our cost function. So it's basically, if I apply it to all data points, I have a summation over n data points, and for this n data points, I have to minimize e to the power of minus yi times h. And h is summation of beta j h j. Okay? right? So that would be basically my additive model. But this additive model is in fact, if I want to fit it this way, but by now I have already computed, this function up to j minus 1. So here is basically, instead of having this summation, I can write it this way. I can say, okay, I have everything up to j minus 1. Then I need to add beta times some, say, phi xi. So that's my additive model. And this phi in boosting is basically my classifier h. Okay? Does it make sense?
Will be hj of xi,
hj.
right?
Yeah. Yes. Okay, so that's basically the cost function that we need to minimize. And we have to minimize to find beta and to find h. Okay. So this is e to the power of minus yi f j minus 1 xi times e to the power of minus yi beta j hj xi. Okay, and I want to minimize over beta and h. So if you look at this first term, there is no beta and there is no h here. So with respect to my variable, it's a constant, right? So when I want to minimize this, this is going to be constant. Has no effect in the minimization. So this is constant with respect to my variable. I call it wi. So we need to minimize wi e to the power of minus yi beta j h j x I. Okay. Okay, let's try to simplify this. Yi could be equal to hxi. If yi is equal to hxi, then yi times hxi is 1. Otherwise, it's a negative 1, right? So I can write this summation as summation, this is summation over all i's. I can make it as summation over i's such that yi is equal to hxi. For those that yi is equal to hxi, this is going to be wi e to the power of negative beta. Okay. I just dropped this j, but to make our notations simpler, but it's beta j, this is hj. We are just learning a coefficient and a class for this particular iteration. So it's e to the power of minus beta plus summation of the points that these two are not equal. If these two are not equal, then this is going to be h times y is going to be negative 1, and it's going to be e to the power of beta. Okay? It's clear here? So basically, it's going to be e to the power of negative beta summation over wi for yi equal to h plus e to the power of beta summation over wi for yi not equal to h. Okay. So I will write it as e to the power of negative beta summation of wi I yi equal to hxi over all I. I write this first term this way. And I write the second term e to the power of beta summation over all I of wi I yi is not equal to h xi. Okay? Does it make sense? I would like to be able to, factorize it. So I would like to write the first one such that it's in terms of I yi not equal to hxi to be able to factorize this. So yi is either equal to h or is not equal to h, right? So this term, I can write it as all of the w's minus those that they are not equal. It's this term. That was only that are not equal. Sorry, only that are equal. I write all of them minus those that are not equal. Okay, plus e beta I wi I yi not equal h xi. Okay. So if I apply this to this bracket, it's going to be e to the power of minus beta times this minus e to the power of minus beta times this plus this. So what is this? This is my cost function. And I have to minimize this cost function and find beta and h. So we need to minimize this, find beta, and find h. So let's take derivative with respect to beta and set it to 0 to compute beta. Okay, derivative of the first term with respect to beta. So what's the derivative of this term with respect to beta? Sorry? Yeah, the same term, exactly, with a negative sign. So you need to take derivative of this. E to the power of minus beta would be negative e to the power of minus beta. And so the first term would be negative e to the power of minus beta wi. The derivative of the second term would be plus e to the power of minus beta wi yi not equal to h x, and the derivative of the last term would be e to the power of beta wi yi not equal to hxi. This should be equal to 0. Okay. Did I miss anything or think? No. So this should be equal to 0. So it means that e to the power of, I'm going to take this term to the other side and divide everything by sigma wi. So on the right side, I'm going to have e to the power of negative w summation of wi I yi not equal to h xi divide by summation of wi plus e to the power of beta wi yi not equal to h xi divide by wi, and on the left hand side it's going to be e to the power of negative to the power of negative beta. Right? Yes.
You said wi equals minus I times f minus 1 of xi. Fg minus 1 xi.
Which one you are taking?
Wi, I mean that actually
Here?
in wi, yeah, wi.
Okay.
Instead of wi by e minus 1 yi times fg minus 1 xi. Wi. Just
Wi times this.
the above one.
This one?
Yeah.
Okay.
In wi, actually, it also includes beta.
No, it doesn't.
Yeah, fj minus 1.
But fj minus 1 is a model that you have already computed. You compute one base at a time.
Yeah.
So for the first base that I computed the beta corresponding to that one. For H1, I computed beta 1 already. For H2, I computed beta 2 already. And then I add them up. This is my function. So at each stage, this fj minus 1 is a noun. The beta corresponding to the base, the parameter of the base, everything has been learned already. So there is nothing unknown here when I minimize. It's fixed, it's constant with respect to my variable. Okay?
So here G means usually
Sorry?
of the G.
G?
G minus 1 G.
Oh, J. So fj minus 1 means all of these summation up to, we have this definition here. All of the summation up to j minus 1. All of the summation here. This has been already computed. This is fixed. In the next step, you just add this one. This is already learned with all of the parameters. Okay? Is it clear? Okay, so let's get back here. So do you agree that if we take derivative, set it to 0, then I have to solve for this? And what is this term? It's LJ, right? It's weighted error. So basically, this is LJ. Okay. So I can say that LJ is in fact so LJ times E minus beta plus E beta is E minus beta. So Lj is E minus beta divided by E minus beta plus E beta. So I need to solve for beta. So because we took partial derivative with respect to beta, set it to 0, I need to solve for beta. Okay. So I claim that if you solve for beta, it has a form like this, log of 1 minus L divided by L, but it's easy to see it. So that's L. Let's compute 1 minus Lj divided by Lj. 1 minus Lj divided by Lj is going to be E minus beta plus E beta. This is 1. E minus beta plus E beta minus Lj would be E minus beta divided by Lj, which is E minus beta, and denominator would be the same. So this denominator will cancel. This will cancel. It's going to be E beta divided by E negative beta, so it's E2 beta. Take log from both sides. Log of 1 minus Lj divided by Lj is 2 beta. So 1/2 of this is going to be beta. So if you compare it with our algorithm, alpha is basically 2 beta, right? So alpha is 2 beta. Okay. When I'm fitting the new bases, basically I'm computing this, right? Wi, which is constant up to the previous step, times e to the power of minus y beta h. Okay? So in fact, adding a new basis, suppose that I go to a step k. This is k minus 1. This is for a step k that has been added. Now if I go to a step k plus 1, this will be a part of w. I have another base here. This goes to the summation. It means that in each iteration, wi would be wi times this part from the previous step becomes a part of w of the next step, right? So it means that wi in each iteration is going to be wi times e minus yi beta times h xi. Okay? So if you want to double check because I want to erase. So in each iteration, my w is going to change this way because I'm going to add a new base function. New base function means the previous one becomes a part of the weight now. Okay. Yi times h xi, negative yi times hi, is either 1 or negative 1. If they're the same, it's going to be negative 1. If they're different, it's going to be 1, right? So I can write it as 2i yi not equal to h xi minus 1. If they are not the same, then it's 2 minus 1 becomes 1. If they are the same, it's a negative 1. Right? Okay. So my new W is going to be W times e to the power of, instead of yi times h, I will put this. It's going to be 2 beta I yi. It's going to be e to the power of beta times 2i yi not equal to hxi minus 1. So it is wi times e to the power of 2 beta I yi not equal to hxi minus, I have here minus beta means e to the power of minus beta. Okay? So 2 beta is alpha. So this is alpha. So compare it with our scheme for weighting the change, changing the weight, not weighting the change, changing the weight. It's wi times e to the power of alpha I for those that have been misclassified. It's exactly the same. E to the power of alpha I for those that have been misclassified. But I have an additional term here. Does it matter? I mean, does it make this algorithm different from that algorithm, this part? You know, we want to reweight all of the points. We want to give higher weights to points that have been misclassified, right? This is a constant with respect to the fact that the point is misclassified or is not. Okay? It doesn't matter. So if this is my weight, that would be identical to the weight that I have in Adaboost. If I multiply all of the weights by a constant, doesn't matter because eventually I'm going to compute this weighted sum. You know, whatever the weights are, you know, I'm going to take the summation of them and divide everything by that summation. So I'm going to normalize it anyway. So it doesn't matter if I multiply all of my weights by 100 to whatever. So this is a constant which is going to be multiplied to all of the points. But this is a part which makes sure that the points have been misclassified should be given higher weight. So I can literally ignore that part. So it doesn't matter. Okay, so compared to this, we exactly compute the same scheme of weighting. And what we compute here at the final classifier would be exactly the same. You know, what has been learned up to stage j minus 1, add a new one to it. And this new one is what? Is a classifier which has been learned by minimizing this and with this coefficient. So we have the same coefficient, we have the same weight, we have the same cost function here. So basically you can think of boosting as a way to feed an additive model to the data when your bases are classifiers. So basically, I'm asking that how good this can be fitted by this classifier. There's some residual, some of the points left behind, they're not fitted well. So I feed another classifier to take care of that. Again, some points are are left behind. I feed another classifier to feed that. So I'm learning a additive model, and end of the day, actually, this additive model is supposed to do better than the original one, and it does. Does it make sense? Okay, let me show you. See, this is my data point, and I want to classify them. Suppose that I have a very simple classifier, and that's the classifier. Decide that all of these points are red and these points are blue. So clearly some of the points have been misclassified. So I add another classifier, and this second classifier, when I want to add the second classifier, I give more weights to points that have been misclassified. This point is in the wrong side. I give it more weights. You can see it's larger, and those are smaller. So I give more weight to this point that have been misclassified. So if I give more weights to these points that are misclassified, now if I want to learn a classifier, just a line, to classify them, what would it be? It would be a line here, to put these 2 points on one side and this point on the other side. So that is basically my second classifier, That's my second classifier. But my classifier after these two steps would be aggregation of these two, weighted aggregation of these two. If you look at this yellow line, would be aggregation of whatever we have so far. And then I can add another classifier. See, the third classifier basically would be this one. Because, in this step, there were some points that have been misclassified. We give them more weights, and then that's our third classifier. But third classifier combined with previous classifier give me a decision boundary of this form. And I can add more and more classifiers to this. And if you look at the error, you can see that this is training error, this is test error. You can see that this goes down. But the interesting thing is that it's hard to make boosting overfit, if I just add and add and add. So it may overfit eventually, but it's very resistant to overfitting, It doesn't happen soon. See, I add more models, and it's sort of stable. It doesn't jump up, Training error goes down, but test error doesn't improve, but doesn't go up as well. Okay. Let's do another example. So that's my data. It's like a circle. And I use my classifier to be a tree. So a tree classified this way, And then I add a learner. I can get rid of this plot error. Don't want error. So that's my classifier. That was original data. And that was the first classifier. That was the second classifier. And then I add more and more and more classifiers to it. The training error goes to 0 and test error, it's sort of stable, again, doesn't overfit easily. Okay? Any question? It's very common to use boosting with tree because the cost function of tree led you to apply this weighted form easily. In general, how do you apply this weighted form? Suppose that, for tree it's easy. For tree I have to basically count the number of points on one side and the other side, so I can make it weighted. Instead of just counting the points, just make it weighted. It's easy to apply. But in general, how do you apply this? You have a cost function for SVM. You are going to learn, a quadratic. You are going to solve quadratic programming and find a function. So, in quadratic programming that you have is not weighted. How are you going to weight this? You have to sample from training data according to your weight. Make a new training set. So basically, you apply this weight implicitly, not explicitly. You don't change your algorithm. You use the algorithm that you have. You change your training set data and give it different weight. When you start, points on your training set have all the same weights. So suppose that I have n weights, n data points. So the weight of each data point would be 1 over n. For n data points. Now, I compute the weights for each data points. And I need to train my model according to this weight now. So instead of explicitly apply this weights to my learning algorithm, I'm going to sample from training set and make a set which give more emphasis on the points that have more weights and less on those that have less weights. Okay, so some of the points are going to be repeated in this data set. So from one point, going to have many of those because it has high weight. And to do this, to do it systematically, you can do it in many different ways. But a very simple way to do it is to use rejection sampling. Now, for rejection sampling, suppose that this is the density. This is the density of the function that eventually I want to sample from. This is my proposal distribution. That's the idea of rejection sample. How many of you are familiar with acceptance rejection sample? In acceptance rejection sampling, I have a distribution which is hard to sample from. But I have a proposal distribution which is easy to sample from. Say the easy distribution is this. The idea is to find a constant number c. I call this f. That's the hard one. I will find a constant c such that c times g x, this is c C times gx. I find the constant C such that C times gx is greater than equal f of x for all x. Okay? Then I sample from G. If I sample from G and I accept it with probability, accept Y with probability F divided by C times G. And if you want to implement this, basically you can do it this way. You can sample a U from a uniform distribution between 0 and 1. And if U is less than equal F divided by C times G, accept it. Means X is Y. Else, go to 1. Go to a star. Sample another point. And C could be any number that makes C times G greater than F for all points. Okay? But the greater the C, the larger the C is, the less efficient your algorithm is going to be, because this probability is going to be smaller, and you're going to accept with this probability. If it's a smaller one, you're going to reject many points. So you have to choose C wisely. And the best C is C which maximizes f of x divided by g of x. That's acceptance rejection sampling. It's very easy to apply it here. Just pretend that this is your G, this is your F, and you want to sample from this. Computing C is max F divided by G. So these are discrete, both of them are discrete distributions, right? And these are numbers. You can basically divide each of these numbers by this number and see which one is larger. Choose that one as your C. So you have your C to be efficient. And then first step, you have to sample from G. How to sample from G? It's uniform. Means choose one of these points randomly, uniformly. From your training set, select one of the points uniformly. So you're going to select one of the points uniformly from your training set, and then sample from uniform between 0 and 1. In MATLAB, you just say, rand. It makes, a point between 0 and 1, uniform. And if this U is less than, suppose that you have selected this point, and this point is at its position I. If this is less than this quantity, accept it. Means put it in a new set. If it's not, don't accept it. Go and choose, take another one. And run it for a while. You're going to have a training set which respect this set of weights. Points that have higher weights are repeated more. Points with less weights are repeated less. Okay? And then you do your training with this. You use your original algorithm to learn. You don't need to modify your algorithm. It's useful also for the case that you have imbalance points. You have two classes. In one class, you have 20 points. In one class, you have 200 points. It's usually any classifier is going to break if you apply it directly. But you can oversample from the rare class, have more points for that class using this technique. So first of all, I didn't say that it doesn't overfit. I said it's hard, actually. Resistance to overfitting. It does, it can overfit, but it's resistance to overfitting. So There are many theory behind that what's happening. I just showed you that boosting can fit an additive model. You can show that boosting compute a maximum margin classifier. Okay. You can show that, in each iteration, basically you're maximizing margin between these two classes. And if you maximize the margin, it has a very good generalization bound. Means it's hard to overfit, when you have maximum margin. So you can show that theoretically again, but same as this one, it has a proof which shows, the margin becomes large. I mean, when people realize that it really works very well in many cases, then I started to think that's why it works. And you can sort of appreciate here that the proof that we went through was not the original, idea of inventor of boosting, And you can see that it is in fact somehow artificial, the way that we are showing the connection, we choose a cost function e to the power of this, which is a good cost function, but it's not a common cost function that we so far use in classification. But based on this understanding, there's many other type of boosting suggested afterward that they are different in the way that they define the weights, they define the cost function, and they use different type of different type of cost function here. And some of them are designed specifically to really make sure that this margin is maximized. And one of the reasons that it doesn't overfit easily is that it is basically a maximum margin classifier. SVM has a very good generalization bound. And not the same bound here, but you can show that it's a very good bound actually exists here for the boost. Okay, any question? Okay, see you next week.